Hello, this is Chapter 9. This is Section 9-2. This is recording number 1. All right, folks, where are we? Section 9.1 is testing the difference between two means using the z-test, and we can only do that if we know the standard deviations or the variances for the population, okay? Okay, and I mentioned to you that there is a page in your book that gives the important formulas, and here it is. This is the page from the 9th edition, but there's a similar one for the 10th edition as well. So gosh, I'm trying to get this a little bit bigger for you. Here we go. All right, so what we've done so far is this formula right here, and as you can see, we know the sigma for each of the populations, sigma 1 and sigma 2. If we know the sigma, then we can use the z-test, and that's to do the hypothesis testing. That's to do the test value and compare it to the critical value. In addition, as the author pointed out, we are considering the delta. I mentioned that last time. Delta means the difference. So the delta of x bar 1 take away x bar 2. That delta can be considered as a random variable. Okay, it has its own distribution. That's the whole premise behind using the z-score. So if we're interested in this delta here, the mu1 take away mu2, we can use as a point estimate for this distribution, for the mu1 take away mu2. For this delta, we will use as a point estimate this delta. We'll use the x bar delta as the point estimate. And just like we did before, when it comes to interval estimation, the way we get an interval is we say that the interval is the point estimate plus or minus the margin of error. Okay, so here's the margin of error. It's plus or minus the margin of error. So this is a way for us to get the confidence interval for the delta of two means if you know sigma 1 and sigma 2. Now, it's a little bit confusing sometimes because here we're talking about the means of the population. Here we're talking about means of the x-bar means, the means of the sample. Just keep in mind that the whole premise behind this is that we're trying to decide if we have a difference between these populations. We look at samples. The samples represent the populations. So when we pull the samples out, we are asking ourselves the question, is there a significant difference between the samples? In other words, is there a significant difference between the populations? So pick whatever example you like. You're testing a brand A, you're testing brand B. You take the medication, you don't take the medication. So are those two different populations or not? Does it make a difference whether you use brand A or brand B? Does it make a difference whether you take medication A or take medication B? Does it make a difference if you take a medication and you take a placebo? Those are the kinds of questions that we're trying to answer here. And we're doing this, if we know the sigmas, we use the Z formula. If we don't know the sigma, then we're going to use the T formulas, okay? So that's kind of the overview. Again, I'm sorry to keep belaboring this point, but I've just found people have such a hard time with these concepts that I think it's worth a few minutes to discuss it. That way, and what's really great on video is you can stop the video, you can rewind it, you can Google any words that I use. It's really a very efficient way of learning this material, in my opinion. Okay, so now we're going to get into 9.2. 9.2 is going to be using the t-test, and this is where we do not know the population standard deviation or the standard deviation. I'm sorry, we do not know the population standard deviation. We do not know the population variance. Okay. The one condition we do have is they have to be independent samples, and we'll discuss that here in just a minute. An obvious question would be, what do we do if we don't have independent samples? Well, we can still use the t-test. We can still use the t-test, and it's from the dependent samples, but as you can see, it's a different formula. We use the t-distribution. Here it is, t-distribution, just like up here, this t-distribution. However, the formula that we use is going to be different. Okay, so just like before, we consider the mu1 and the mu2, or the mu1's take away mu2, that delta mu can be considered as a random variable. We may wish to estimate it. The way we estimate it is we find the point estimate. The point estimate is the x bar 1 take away x bar 2. So it's the delta of the x bars. That's your point estimate. And then you have plus or minus the margin of error. Here's the margin of error. It's the standard error multiplied by this. I would call this a coefficient. It's the t-value that is appropriately chosen based on what you want in terms of a level of confidence. Okay, so that's the overview. I hope that makes sense to you now that we've done a little bit in chapter 9, but we've done all of chapter 8, and these concepts are very, very similar between chapter 8 and chapter 9. And in fact, that's why I've been beating on this dead horse so much, because I find that students have a real hard time keeping the concepts different, or keeping the concepts straight between chapter 8 and chapter 9. Okay, so here we are, chapter 9, section 9.2, and it's independent samples, and we're going to use the t-test. So here we go. Let's take a look here. All right, so as the author says, and by golly, I hope you're reading this material ahead of time. In section 9.1, we use the z-test, and that's when we know the population standard deviations. Now, do you see why language is so important in mathematics? It's the population standard deviations. Obviously, we know the sample standard deviations. We have the samples, right? It's just a calculation. So it's the population standard deviations that we may or may not know. And in section 9.1, we are assuming that we know the population standard deviation for whatever reason, okay? Let's not quibble about whether that's a legitimate assumption or not. Okay, so get some other conditions here. One of the conditions was, of course, the population standard deviation. It has to be true that the variables are normal. The original variables, the original random variables, are normally or approximately normally distributed. I've seen other texts that say that all it has to be is symmetric. It doesn't really have to be normally distributed. So, whatever. And this author says it has to be approximately normal. And then both sample sizes have to be greater than or equal to 30. Okay, so it's in the disjunctive here. Disjunctive. It's disjunctive because it's one or the other. It has to be approximately normal, or if the sample sizes are greater than or equal to 30. Okay, so in many conditions, these conditions cannot be met. Maybe the standard deviations are not known. So in that situation, you use a t-test. And let's see, a t-test is used to test the difference between two means if the two samples are independent. So they do have to be independent. That's a hard requirement. And then the samples are taken from two normally, or at least approximately normally distributed populations. Okay, and then we talked about before, when do we say a sample is independent or not independent? It's either independent or it's dependent. So this is the scenario where they are dependent. Okay, so here's the formula. It's the same basic concept. On top, in the numerator here, is the observed value, take away the expected value. What I call how surprised are you is on top, and on the bottom is the standard error. That's your yardstick. So if I were you, I'd write this down. I don't have it written down. I can't write it on the screen here, of course. Write it down on the t-test, or the test value, excuse me. The test value is how surprised are you? That's what's on top. How surprised are you over yardstick? The denominator gives you a yardstick that tells you what the top really means. Okay. So now we got this comment here, the mu1 take away mu2 right there, that is typically, not always, but typically that's equal to 0 and the reason why is because our null hypothesis is typically, mu1 equals mu2. That's kind of a standard way of structuring the test. Okay. All right. So this bottom guy here, that's the standard error of the difference. That's the standard error. We call that the standard error of the deltas. Okay. All right. So he's not going to derive this. Now, give me 1 second. So what's the big difference here between the formulas here? The big difference. You look at this one. And then, like I say, it's a lot easier if you have your book right there with you. Look at that. Compare that to what we had before. They're almost identical. The difference is on the first one, on the z-test, we use sigma, whereas on the t-test, we're using s. That's the difference. Okay? Another nuance to this that I just want to share with you is we've got a situation, he just kind of mentions it in passing. Here we go. Also, it will be assumed that the variances are not equal. Okay? So he's talking about the variances of these samples down here. An obvious question is, well, what if they are equal? What if it just so happens, you're talking about some sort of a random variable where the two population or the two samples that you pull out just happen to be that they are equal. I mean, it could happen, right? Okay, so the answer to that question is what happens if they're equal. There's a different formula, but that's beyond the scope of this book. Okay, so it's a different formula, as I said, and let me tell you what I do when, as I'm reading a textbook or whatever. One of the great things about online learning, in my opinion, is that you can Google everything. So I Googled this question. I thought to myself, it's funny that the author mentions that they're assuming that you have equal sample variances, but what if you don't? So I Googled that and I came up with a couple of websites. So then what I do is I copy and paste the web link, and then I email it to myself, and then of course I put a little bit of a title up here so I know what the heck I'm talking about here. And then here's my subject line. So I used to email this to myself the other day. So here it is. So now I've got it ready to go if I ever need it in the future. Gmail is so great. It's very, very easy to organize things. So in any event, here's the answer to that question. What happens if you have equal sample variances? And then here's the same from the same basic website, from the same website is a different page. This is what happens if you have an unequal sample variance. So if it's an unequal sample variances, well, then we just do what the author says to do. This is where you have equal sample variances. So let's take a look at that just real quick. You're not responsible for this, but I'm just trying to show you how important it is that you take, basically take responsibility for learning this material on your own. There's infinite amount of material to learn. Just kind of expand your horizons a little bit here, if nothing else. Okay, so here we go. Equal variances. Okay, so now I'm having a hard time with this crazy program here. Let me see if I can get you lined up here. All right, I think you're on this. I think it's on the screen now. So this is a good website. If anybody wants it, I'll be happy to send it to you. But it's called real-statistics.com, and then they, obviously they have a directory. You can find all kinds of stuff. So as you can see, it has quite a bit of stuff here. Okay, it's talking about distributions. This is analysis of variance. We're going to cover that very briefly at the end of the term. Okay, here's regression. Here's multivariate. All kinds of good stuff in here. So here's about the sample t-test. Okay. And then if you have equal variances. So here we go. This is the formula if you have the same variance. So there's a different formula. Okay. That's the only point I'm trying to make. So don't worry about it. We're not going to be responsible for that. But I just wanted you to know that there is an answer to that question. All right. So that's the end of this recording.